In this video, as part of Bayesian learning, we will study Bayesian belief networks. In many cases, the attributes may be such that we may be able to apply conditional independence, but not in complete form. If you can recall, in naive Bayesian classifier, the complete conditional independence was applied. For all the attributes, conditional independence was applied. There are many cases where conditional independence may be existing among a subset of variables only. Bayesian belief networks are structures that allow stating conditional independence that apply to subsets of the variables only. Bayesian belief networks provide an intermediate approach which lies between global conditional independence made by the naive Bayes classifier and avoiding conditional independence assumptions altogether. So it's an intermediate approach. A Bayesian belief network, or shortly called Bayesian network, represents the joint probability distribution for a set of variables. For example, the Bayesian network in this figure talks about conditional independence among storm, bus-2 group, campfire, forest fire, thunder and lightning. It talks about the joint probability distribution over the variables storm, lightning, thunder, forest fire, campfire and bus-2 group. In general, a Bayesian network represents the joint probability distribution by specifying a set of conditional independence assumptions and conditional dependence assumptions. So, tables are given for the variables to represent conditional probabilities for the variables. In the figure, where each variable has been represented as an ellipse, each ellipse is a node or a variable. Each variable may have parents and descendants. We say campfire is a descendant of storm and bus-2 group. We can also say that storm and bus-2 group are parents of campfire. We will say campfire is conditionally independent of lightning, thunder. We will say thunder and forest fire are descendants of lightning. For example, for campfire, parents are storm and bus-2 group, and for lightning, descendants are thunder and forest fire. Campfire is conditionally dependent on storm and bus-2 group, but independent of other attributes. We say X is a descendant of Y if there is a directed path from Y to X. Basically, this network is an acyclic directed graph. Acyclic directed graph. It is acyclic because there is no cycle notion here. And it has some direction. The arrows have some directions. For example, this particular arrow is directed from storm to campfire. For each variable, two types of information are specified. Firstly, the network arc says a descendant is conditionally dependent on its parents, that is, origins of arcs. Secondly, a conditional probability table is given for each variable, describing the probability distribution for that variable. The Bayesian network in the figure represents the joint probability distribution over the Boolean variables: storm, lightning, thunder, forest fire, campfire, and bus to group. In this, once we know the value of the variables storm and bus to group, the variables lightning and thunder provide no additional information about the campfire, because campfire is conditionally dependent on only storm and bus to group. It is conditionally independent of lightning and thunder. Let's understand this with an example. So the background information is, there is a house where a security system has been installed. An alarm is expected to sound when there is either burglary or earthquake or both. John and Mary are neighbors of the resident. John and Mary will call the resident of the house after hearing sound of alarm. The questions are, what is the probability that alarm sounds when there has been neither burglary nor earthquake, and John calls and Mary calls? The second question is, what is the probability that John will call? So the network, Bayesian network corresponding to the given problem is, alarm is dependent on conditionally dependent on burglary and earthquake. John calling is dependent on alarm. Mary calling is dependent on alarm. So we give the probability for burglary. That is a standalone probability. There is a probability for earthquake. This is also standalone probability. But as far as alarm is concerned, we will write a conditional probability. And for John calling, we will write conditional probability because it is conditioned with respect to alarm. And alarm is conditioned with respect to burglary and earthquake. Similarly, Mary calling is conditioned with respect to alarm. So there is a table for conditional probability of alarm. P of A given B and E. If there is a burglary, it will be called true. If there is no burglary, it will be called false. So there will be 4 options for B and E: true, 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 false, false, true, and false, false. And we assign the probability. The assignment of probabilities, assignments of probabilities are based on experiments. Similarly, we assign probabilities for John calling and not calling, conditioned with respect to alarm, P of J by A. Similarly, for probability for Mary calling. So if you see, every variable is associated with a probability table in general. So the first question is asking for joint probability of not B, not E, A, happening of A, then happening of John calling and happening of Mary calling. Because the question is this: what is the probability that alarm sounds when there has been neither burglary, that is not B, nor earthquake, that is not E, then John calls, then that is J is true, and Mary calls and Mary is true, and alarm sounds, A is true. So we have to find the joint probability of these events: P of not B and not E and A and J and M. This is equal to probability of John calling given A and Mary calling given A. Now A is conditioned with respect to not B and not E, because here the question it is mentioned neither burglary nor earthquake. So P of A given not B not E into P of not B into P of not E. And if you substitute these values, you will get this value 0.000062. The second question is more calculative. It needs more calculation. The second question comes under total probability. It seems as a standalone probability, but it is basically a total probability. P of J is equal to John calling condition with respect to A, that is P of J by A into P of A, plus John calls on condition with respect to not A, that is P of J given not A into P of not A. Now in this, P of A and P of not A are again total probabilities. P of A is equal to P of A given B and E into P of B and E plus P of A given not B and E into P of not B and E plus P of A given B not E into P of B not E plus P of A not B not E given not B not E. Now we have to substitute all these values here. And we can get the P of A value. Similarly, we can go for calculating P of not A. P of not A is equal to P of not A given B and E into P of B and E and so on. So if we put the P of A and P of not A and P of J by A and P of J by not A, we'll get P of J is equal to 0.0521. I hope you understood how to use this Bayesian belief network to a simple problem. I hope this topic is clear. And if you like it, please give a like for this. Thank you.